Okay, so for today's lecture, we'll start to tie these ideas of regression and all the things that we've been doing in linear algebra for the last few lectures together. First, they'll start with an overview really quickly, maybe like 15 or 20 minutes or so, reviewing the last couple lectures together and bringing it all together to set the stage for linear regression. And remember, always post any questions you have on the Q&A or forms for the COG or the DSC40A class, and we'll get to them as soon as possible. Okay, so going back to this idea of spans and projections. So we first started off by thinking about this idea of a single vector, and we wanted to find the projection of y onto the vector x, and particularly we wanted to find some w that we can use as a scalar to change x. And this winds up giving us here some vector in the span of x. And right now, since x is just, we only have one x, that being in the span of x is, it means just we're along this line, either going this way or going this way. And the vector could be, anything of any length. But the best vector, the w star that we want to get, is the one that makes the projection of y onto x be orthogonal. So that's what we're looking for. Okay, and once we found that, what that w star was, is it wound up being this sort of somewhat scary looking quotient here. We have four vectors, but really all this is it's just a scalar. So w star is just a scalar, and ultimately it's just what we're using to multiply x to get it towards orthogonal with y. So remember, so how do we get what w star was? Well, we had to find out whatever w, since we know w star winds up being a scalar. When we take that and let's write it out, actually, that would be probably better. So okay, so where, and this is what the E is, the error is. So this thing is kind of E. So wherever we have the x vector dot product with the E, and that equals 0, which means that they're orthogonal, that's how we found out what our W is. Because if we want to make W star the scalar that sets the vector of x to being orthogonal with E, then that's the best W, and that can only happen under one condition, and that's when the dot product is equal to 0. Okay, so next we had this idea of kind of moving from one vector into multiple vectors. And this is, remember we had that video that Jack had created for DSC40A in the spring with this idea of two vectors that span this plane. And that's what this plane is here. And we say that the vectors x1 and x2, so x1 like x2, they span this entire plane. So maybe to make it a little more explicit. Okay. And we wanted to know what is the vector that we can get where we say that this is E so where E is orthogonal to the plane, or in this case, x1 and x2. And where it's orthogonal winds up being the projection. Maybe we'll put this one in green, which, well, maybe we'll do black since this line's already in black. So that would be the projection with W1 star plus W2 star. Oops. And that's the projection. So this idea here is that we want to find out what this E is, and we do that by finding the best W, and we can do that for each of the individual X's. Yeah, I think that's probably pretty good on this. I think the key thing here to really think about is how do we think about this stuff? And it's not too bad when we have two X's like x1 and x2, but of course we want to come generalize this whole process to when we have multiple X's. You know, any number of them. Could be 50, could be 100, could be 10, because this idea of finding this projection here where we have W1 star, W2 star, we don't want to have to kind of do this for any number of X's that we have. We're always going to have one Y because Y is just one vector, and the length of its vector is always going to be the same or equivalent to the number of X's that we have, because that's our dimensional space that we're in. But we really want to be able to take this concept and transform it into being able to work with a number of vectors, a number of X's that we have. And so to do that, we introduced this idea of using a matrix. So we had, in this case, x1 and x2, and we took those vectors and we stacked them column-wise into a matrix X, and we used that to, well, that along with like the dot product and matrix multiplication to have a nice way to kind of generalize how to deal with all that data being the different X's. We're always going to have one Y, and that Y vector is going to be the length of each of our X's. And then we're always going to have a W vector that we're trying to figure out. That W vector is going to be whatever the number of columns that we have is. So in this case, I'll write it down. We had this, which was a 3x2, and our W1 and W2, which is going to be a 2x1. And we can multiply these because it's a 3x2 times a 2x1. And that's going to allow us to do these multiplications and find that those W's essentially. And if we look back to this equation right here, this is looking at the length of vector E is going to be equal to the length of whatever our Y vector minus these linear combinations essentially of x1 and x2. But here we can rewrite it in a much more clean way. And the reason why we can do that, of course, is just because in this case, I don't probably need to write the whole thing out. This in the next slide, yeah. But just very quickly, we have this x w, which is equivalent to w1 x1 plus w2 x2. Okay, so that was the whole reason why I brought matrices into the mix. And once we have x as a, as our column vectors, we can do some very nice operations with it, such as transposing, and that will allow us to resolve a bunch of these issues. So we know next, once we have this idea of being able to keep these vectors into a matrix, that we need to begin to work with them, because we want to find X transpose times E, and that gives us our W star. Where X transpose T times the error vector is equal to 0. That tells us, because of the dot product, that we can take that E vector and multiply it individually by every single X vector that we have, and that will tell us where the projection is orthogonal from E onto our X's. So let's see. Why can we do that? Well, remember that we have our original vector X, or matrix X, was a little bit larger. We had X1 and X2, and then this of course gave us and so we took the transpose of that, and once we have that transpose, we're able to do that dot product of the E vector onto each of the individual X's that are also essentially transposed. So this allows us to kind of, actually do it in purple. This is a 2x1, and all these individual ones, I can do this a little better, are just some X dot product with an E, and that's all it winds up being. Really, all this being this right here, is just a vector, and it equals really the 0 vector. So this is the same thing as saying X transpose times, remember the E vector here is just a stand-in for Y minus W, well, I suppose, yeah, X times the W, and that equals 0 because this is where they're orthogonal. We're essentially taking each of the taking the dot product of every single one of the rows of this guy with our error, and when we do that, we can find out where the error is orthogonal onto the projection of each of the X's, and that gives us our optimal scalar, or W star. So right now we're at this point where we know that we're working in multiple dimensions. We know that we need to take our X vectors and we need to stack them into a matrix so that we can use that object to solve for the W star. And what we essentially got when we did that was this idea of the normal equations, and with the prime one of these, this guy right here, the whole output of that was a system of equations. And the system of equations that we got out of this, so we had this equation here that we can use to find W star, and since we know that we can take this E and replace our error vector with the Y vector minus the stacked columns of our X vectors times some W, and if we put that in for E and we set whatever that W we want to find is, the W that we want to find is the optimal W, the one that satisfies the orthogonality between the projection of Y onto the X's. And we know that if we set that equal to 0, that's where it's orthogonal. So that in order for this equation to be satisfied, for this to actually equal to 0, this has to be W star. It can't be anything else, because that's where it is orthogonal. And so if we substitute in this for our E, and then we do a little bit of let's write it down so we remember them. We do a little bit of distributive and rearranging. Right, so we distribute out here, rearrange a little bit, and we can take, essentially we can take x transpose times x and the inverse of that and multiply it by both sides, which will essentially get rid of this. Oh, there we go. So sorry, if we take the inverse of this right here, which is just going to be x, would that be x transpose? Yes, x transpose x negative 1. We multiply that by both sides. We cancel that out, and we have essentially just this, and that allows us to isolate the w star, which gives us this thing right here. So that's where we have, this is over here, and then we have the inverse of it that we multiply on both sides to get rid of that. Let's write that out because it's good to know. Essentially, if we take xt x negative 1 times xt x w star equals xt y, we're going to essentially take that and remove that, and then it's going to come over onto this side, which is where we get this. So that's how we isolate for the w star. Now we can only really do this if x transpose x is invertible, and a big assumption of that is that it has this idea of being full rank. Right, and full rank is just one way of saying that all the columns are linearly independent. So for our x, all those column vectors, the x1, the x2, and all the way to xn has to be linearly independent. And we know that a series of vectors are linearly independent if the only solution to setting a scalar to each individual vector is equal to 0 if the scalars wind up being 0. So that means that no other vector in the set can be written as a linear combination of the others. So this is a this idea here is important because if there isn't, or if it can't be, maybe I'll write this down. Just it's good. So full rank means that all columns are linearly independent. And what we mean by if it's not full rank, then there are infinitely many solutions to normal equations. So what we mean by that, well, it doesn't mean that you can't find like the minimization and that where the projection winds up being. It doesn't mean that that doesn't exist. It also doesn't mean that you can't find like a best fit line when doing regression. So let's say we have like 2 dimensions and we're trying to find the best fit line for that data. Just because it's not full rank and it means that there's infinite answers to the equation doesn't mean that we can't do that. All it means is that there's just infinite many w's that can satisfy this idea. Like there's infinite many of these. So that's the key idea there. Another thing it doesn't mean, it doesn't mean that if you have x1 and this is y and that's orthogonal, it doesn't mean that the y vector is orthogonal to 1 or any of the x's as well, or not necessarily. So we really just mean that there's any number of w's that we can find for that satisfies this equation. So that's just something else to keep in mind. Kind of the big picture here is that we're trying to find out what the two w's are, w1 star and w2 star. So that would be essentially this and this. What are those two scalars that we can use to multiply x1 and x2 to make it as close as possible to y, as to where it's orthogonal? So that's the key thing here. That is what the main thing we're doing is trying to solve to find these two numbers. Nothing more, nothing less. And the best way to do that is using these matrices and trying to calculate W star through this equation here. And we get this through this here, which was derived by understanding that we have to set x transpose E vector to 0. And we get the idea of x transpose E vector from here. And we know that that's what it is. And we know that we can count on the E vector by giving us the W's, because we can multiply the E vector individually into each of these X's. And we saw that from previous lectures. And really the main thing that we've done here is a roundabout way of doing an optimization problem. We're trying to minimize some error. In this case, like this function here says that for any W, we can minimize that by finding the length of the Y vector minus the X matrix, or the column vectors that are stacked together, multiplied by some W. And that gives us our W star. Now, why we do this with linear algebra? One of you may have heard of other things like gradient descent, or other types of ways to solve for these loss functions to get a best fit line. And it's true, you can use calculus to do this type of stuff, and we'll kind of see that later on. But it's really important to get an idea of, like, from a linear algebra perspective, how do we do this? This is going to help you a lot in like DSC80 and the DSC140 series, where you have to rely a lot more on linear algebra when doing many more machine learning type of problems. So this is kind of a really good fundamental kind of foundational insight, and to build intuition into these properties of solving a minimization problem with linear algebra. So that's kind of why we've spent a couple lectures on this. It winds up being very, very important. But okay, let's go ahead and move on to the next thing. Okay, so if this part of the lecture going forward feels slightly disjointed from the last lecture, that's because I had to take like a week or a week and a half pause between that previous recording from the last slide in this lecture and going forward in this lecture, because I had a sinus infection, lost my voice for like half a week, so I wasn't able to do recordings. But continuing on now with this idea of wanting to tie together what we've done with linear algebra so far and with linear regression. The reason why we want to tie these things together is because as we move up in the number of features that we want to model with linear regression, so going from simple linear regression to multiple linear regression, we want to be able to generalize this process in some way and to deal with these extra feature spaces. And the way we generalize that is by using matrices and vectors. And another really big bonus to this of having matrices and vectors is that it allows us to also deal with nonlinear features. So things that are quadratic in nature. And this is really important when we start to, this will be really important for you in future DSC classes, especially when you start working with things like neural networks and you're trying to definitely use features that are nonlinear, represent them with functions that are nonlinear. This becomes very important to have a good handle on your linear algebra. So this is why this is a great foundational thing to learn. Okay, so we did some linear regression and some basics of linear algebra now, and so let's real quick just review this idea from linear regression that we had. And we have this hypothesis function, and we're trying to determine a W sub 0 plus, or W naught plus W sub 1x, and this winds up being, in this case, W naught will be your intercept, and then this will be, of course, your slope. And we've been using a loss function to define or to maybe evaluate what a good prediction is. Remember, this hypothesis function is what allows us to make predictions, and the loss function is how we determine how good that prediction is, right? So we have our y sub I, which is our true value, and then we have some prediction that we've made, and then we're squaring it in this case, squared loss. And then with that, we can use empirical risk to determine basically what is the best hypothesis function that we can make in order to make the best predictions. So that enables us to find the W naught star and W sub 1 star, so the best intercept and the best slope. Let's write these again are the best, and that's due to the nature of empirical risk. So we have that idea, and then another concept that we got from simple linear regression to remember is this idea here, which is whenever you see this, just always think this is an average essentially. Supposed to be our average loss, and these are the important concepts that we've learned so far, and we want to kind of use these tools in order to, if we think back to our original question, which is to predict average or to predict commute time from home to school or work, to school. These are the tools that we use: the hypothesis function, a loss function, empirical risk, to determine what this best fit line is, so that we can make good predictions based on the data from the real world data generating process. And in order to generalize this and go into be able to use multiple dimensions, we have this idea of the length of the vector here. And this is really just a, I'll do it in purple. It's this generalized Pythagorean theorem, as you can say. That we're using, where we see that there's the length of the vector is basically just the sum of a bunch of things squared and then square rooted in this case for the length of the vector, and that looks a lot like what we've been doing here. So we're going to use this in our efforts to generalize this process so that we can go into higher dimensional space and use more features. So how do we do that? Well, let's start by defining a few new terms. And for this, we're going to create 3 new vectors. And really, one vector is just a result of the other 2 vectors. So here we have our observation vector right here. And you'll notice how there's the observation vector is in the real space of n dimensions. That n here, which we see is going to be in all these vectors, is just the number of rows in our data set. I'll write that down. So our observation vector is just a vector that we have, which is reality, essentially like how many minutes it actually took us to go to school from home. So in this case, would be equal to, we could say like, I don't know, 25, 30, and 51, so on and so forth. And these are in minutes. So for our particular problem, so for the problem that we're working on, all of these will be in the units of minutes. So that's our observation vector. Is just essentially is the y in machine learning. Y is canonically the real observations that you're trying to make predictions for and compare against the real world. And our hypothesis vector is what we're actually predicting. So this would be, for example, like 26 and 38 and 55. So we see they're, they correspond this way, 55, 51. So, these are the predictions that we're making against our real data. And then we all have our error vector, which is just taking the components of our y observations and subtracting our predictions from it. And I suppose I should also say that this is a 1 by n, and this is also a 1 by n matrix, and click her value. This is your predicted values, and these are your observed actual values. So the key things here. And the error vector is a way for us to capture the difference between these predictions and observations. And I suppose just to make it clear, this is just your H. Because we get our predicted values through the hypothesis function. So the output of that hypothesis function is our H vector. Okay, so to formalize or maybe make these three vectors, the idea of these three things concrete, let's go through an example. So let's, of course, we have our y-axis here, and we have our x-axis, and let's not pay attention to units right now. This is just a simple example. But of course, this data, if we were following from the same example that we started with, we'd have minutes and home departure. So minutes to school would be our y, so the actual values, and home departure time would be our observations, and then we'd make predictions based on that. So in this case, let's say that we have this hypothesis function here, so 2 plus 1/2 x. And let's go ahead and start by defining what our y vector or observation vector would look like. And to do that, let's go ahead and I'll also say that this is the first, second, and third observation, just so that we can have some consistency in this example. And so our y vector is going to be a 1 by 3, because we have 3 observations. And this is going to be 4, 5, and 2. So just to make that clear, that's where these come from. Actually, I'll probably erase these because that'll get in the way of the line that we're going to draw. But let's go ahead and write those down. So we have 4 and 5 and 2. Okay, so next, let's go ahead and get our hypothesis, or H vector. And for that, we're going to go ahead and determine where all of these x values lie. And we're going to use those and plug them into our hypothesis function and see what we get. So again, we'll have a 1 by 3, which will include a little bit of math. So this will be 2 plus 1/2 times 1. And this will be 2 plus 1/2 times 5. And for our last one, 2 plus 1/2 times 4. Look at our third data point, and we see that the x is 4. 4. So that's going to go ahead and give us 2 plus 1/2 times 1, which will be 5/2. And 2 plus 1/2 times 5, which will give us 9/2. And then 2 plus 1/2 times 4, which will just give us 4. Okay, so now I want to go ahead and calculate our error vector. So this is pretty simple. It's just going to be, I'll just do it like this. So we will have 4, 5, and 2, and we will just subtract 5/2, 1/2, and 4, which will equal, let's see, 4 minus 5/2, that's like saying 4 minus 2.5, which will give us 1.5. And 5 minus 9 over 2 is like saying 9 over 2 is 4.5, so 5 minus 4.5 will give us 0.5. And then 2 minus 4, the real tough one, is negative 2 in this case. So that's our error vector. That is what degree of wrongness our h vector or our predictions were from our real world observed values, our y. And we can take this and actually draw these or display these out. So let's go ahead and do that in purple since our hypothesis function is purple. So we know it's 2 plus 1/2 over x. We also don't need to assume that this is the best fit line. This is just a line. And remember that 2 would be our intercept. So we'll start from 2. And we're going to go 1/2 times x. So it will be, remember, rise over run. So up 1 over 2. So we start here, go up 1 over 2. We'll go to here, up 1 over 2, go to here, up 1 over 2, go to here. So our best fit line will be kind of like this. This is our hypothesis function, sorry, not our best fit line, but our hypothesis function's line will be this. And let's see. So what else is important to go over on this? I suppose that is good for the line. So let's go ahead and take a look at the this guy right here. Okay, so what we observe from our error vector, which is, of course, this right here, and this, well, our yi minus our hypothesis function for each element, right, is what we're doing here. So what does this kind of look like in here? Well, I suppose we can continue in red. I'll just go black. So we have 1/3, right, the 1 over n. And for each element, it will be 1.5 squared plus 0.5 squared plus negative 2 squared. Okay, so this is kind of the connection between what we were doing before and this kind of vectorized approach of describing the error. And what we're really seeing is we can rewrite this actually to follow the ideas that we have from here. And this would really be, this in green, squared hypothesis function. Okay, so we remember we're talking about the length of the error vector, and the length of the error vector is just a bunch of things squared, square rooted, and this is a bunch of things that are summed that are squared, but of course we don't have a square root here. That's nowhere to be found. So we have to square this, and then the 1/3, of course, comes over. And this is how we can define our, essentially, if we go back a couple slides, this is how we're defining our empirical risk in a vectorized format to allow us to generalize to any number of features that we want. So it's just that average loss. And now we see how this is related to the generalized Pythagorean theorem. So that's how these things are related. These things are related through these error vectors that we found. So that is sort of a key thing to take away from here. Maybe I'll put that in green. Key idea. Wow, that's a horrible light bulb. I could try that again. No, I'm like determined. Somehow even worse. All right, we'll stop futzing around with this. All right, so this is the key idea. here. And just to solidify it even more, we have our three vectors. There are three new vectors: the observation vector, the hypothesis vector, which is just a result of our hypothesis function going through the motions of making predictions, and then our error vector, which represents the delta between the observation and hypothesis. And this now represents that, well, at least in this case, we're talking about mean squared error, of course, but the key idea for mean squared error in this case being that mean squared error of the hypothesis function is just 1 over n times the length of the error vector, squared. And we saw that because we did this operation of taking the observation and subtracting the hypothesis, or our predicted values from it. So this is how we can think about mean squared error in terms of vectors, which gives us a generalized way of thinking about mean squared error in multiple dimensions for multiple features. And maybe just to give some context, this is the main thing that we care about, because that represents our hypothesis and observations and the delta between the two of them. Okay, so we want to kind of figure out a way to create some nomenclature around how we can define this hypothesis vector, because this hypothesis vector winds up including all this stuff in it, and we need to be able to package this stuff into matrices and vectors in order to handle it. So it's important to note that each of these rows in your hypothesis vector does represent the hypothesis function. So that's still, in this case, h of x y is equal to w naught plus w sub 1 times x sub I. And this is an n by 1 matrix, and we need some way to kind of unpackage this. And the way we start by doing this is we create two things. One is going to be called a parameter vector. So in machine learning, or a lot of these types of statistical learning type of stuff, we have these things called parameters. So that would be like the w sub 0, w naught, the w sub 1. These are our parameters, and we can extract those out, and we can turn those into their own vector, because this is just a series of w naughts and a series of w sub 1s, and of course this would go on and on and on for as many dimensions that we have. So we can turn this into what's called a parameter vector, which is just going to be parameter w, and in this case it'll be w naught and w sub 1, which is of course a 2 by 1 matrix. Now, if we've put out these w's and we have a 2 by 1 matrix, we know that we need to have something else to multiply. Actually, this is a different color. To multiply this parameter vector. And this needs to be a something by 2, because those inner numbers need to match. Because we're going to take our w naught and multiply it by something here, and our w sub 1 and multiply it by something here. So we have two columns. And if we had a w sub 2, we'd have then a third column. But in this case, we only have w naught, w sub 1. So the easy thing to do is to know that if we want our w sub 1 to multiply some column here, well, in here, it's multiplying x, x1, x2, all the way to xn, and n being the number of rows that we have. So this obviously has to be n. And here we're going to have our x sub 1, x sub 2, all the way to x sub n. Now, the next question becomes, what do we put here? And think about what this is and what this is, we would need to multiply this to keep this W naught valid. This is W naught, this is W naught. So if we want something here to not change this, then what would that be? Well, it'd be a list of ones. And this is true for, in all these cases, your design matrix, for W naught being your intercept. And what we call this thing is a design matrix. Design matrix comes from experimental design, where they build these matrices that would encapsulate all of the information about your explanatory variables when you're trying to create a model of something. So that's where the word design matrix comes from. We're kind of designing an experiment by encapsulating all the variables. So that's where the word comes from. But now we've taken this H vector, which really encapsulated every occurrence of our hypothesis function being used on all of our different x's, and we've packaged that into a design matrix and a parameter vector that we can now use. And using matrix multiplication, we can get back to this thing if we need to. So that's important. So this is kind of a formal way of defining our design matrix, and important to note that y green sub 0 is still our intercept, and w sub 1 is still our slope in this case. And before we had the y vector minus h vector as being our error vector. And we've taken this h vector, which has our hypothesis function kind of built into it, and we've broken it apart into this design matrix times this parameter vector, this x times w vector. So that's all we've done. We've just essentially rewritten mean squared error in this new format. And because h star is kind of this complicated thing that we were dealing with, right? Our h vector, we had to repackage that into something that's more malleable to, using linear algebra. So that's where we're at now. This is what we have. And if you think back to how we originally wrote mean squared error before, this is what we were originally doing. This is the new way that we're now writing mean squared error. And this allows us a really nice way to package a ton of information for our observations and our predicted values from our hypothesis function, and the error between these things all within this nice equation here, which is going to be a lot easier for us to use. So that's all we've done. We've used linear regression or linear algebra to reframe this idea of a mean squared error. So that's what we've done. Okay. So thinking about what we've just seen, we have this W star vector that we're trying to determine, which will act as a way of minimizing the mean squared error that we're currently using. And this is the one that we got from previous slides. And then, of course, this W naught is the best intercept, and this W star sub 1 is the best slope. And we kind of want to think about now, what is the relationship between mean squared error and the length of the error vector? So kind of what's the relationship between this and this right here? And if we think back to the beginning of this lecture, when we started to determine the best W star vector that minimizes the length of the error vector, we can kind of see where this relationship exists. Specifically in our case, we have some X matrix, and we have columns in this matrix that we want to project onto. And the W vector, the W vector that we have in this case is being used to create linear combinations with X. And so we want to know, how do you minimize the length of that error vector? And in the beginning of this lecture, we found that the way to do that is to determine the solution to the normal equations, and that will get us our best W star vector. And specifically using the x inverse x transpose y. And the answer to that will minimize the length of the error vector. And so this is not really like this operation here, the solution to the normal equations is not necessarily doing regression, but it's closely tied to, or it's closely related to the things we do in regression, specifically the minimization. And let's see. I suppose we could write it like this. So this close relationship here can be described as over n times the length of the error vector squared. And the minimization of this mean squared error is going to be the same as the length of the error vector. So if we minimize the length of the error vector, it's the same as minimizing 1 over n times the length of the error vector squared. And particularly, why is that? Where does this come from? Why is the minimization of both these things the W star? And well, minimizing the length of the error vector is the same as 1 times n, or I suppose you just say the length of the error vector squared over n, because if you think back to what we've been learning so far in previous lectures, and some of the things we've done in homework, the fact that we're, and this is not in the general case, but the fact that we're squaring everything, and we know that all of our all the values, well, the length of the error vectors are always going to be either 0 or positive numbers. So if we had multiple candidates for the W vector, then we know that just one W vector was larger than the other. Squaring both of them will maintain that inequality. So that's where this kind of similarity is. Like the 1 over n doesn't matter, and the fact that it's squared is okay, because that inequality is going to stay the same. So even though the outcome of passing a W or W star to this or to this is going to be a different output, the input will stay the same, and they'll both act as a minimization. It's just the minimizer point might be different, but that doesn't change the outcome. It's like when you apply a function, when you have a function that's used and it keeps the order of the values, then the location of the minimum respective doesn't change. So that's fine. Okay. And we see the optimal parameter vector W, and specifically, this is how we used to define our mean squared error. And in order to determine this for the case of one intercept and one slope, we had to calculate W1 and W0 here in a very it's a very lengthy process where we would set the partial derivatives equal to 0, then calculate, and then that would get us our W1 star and W naught star. And we've just found that there's perhaps a different way to do that. And this different way allows us to generalize to multiple variables, and it still holds true for simple linear regression as well. And this winds up being a very nice thing. So this mean squared error here is equivalent to this mean squared error here, and if that's true, and it is, then the minimizers that we were using, which is this, is equivalent to this. So that's kind of what we've shown, and because of this equivalency and I should say that equivalency, we can now generalize a number of vector or any number of columns for x that we want, which is a nice thing. So in order to do this, what we had to do was design or define a design matrix and our observation vector, and then also a parameter vector, which these things are kind of something that we're sort of are kind of like facts of the real world, and these parameter vectors are sort of like the thing that we're figuring out, and that's what kind of like provides that minimization and gives us the it tells the whole story about whether our predictions are any good or not. And this is a nice thing to be able to do. And if our goal is to find predictions that are really good, then the best H vector, hypothesis vector, or that, sorry, in this case would be the H star vector. It's we want to be able to use the best parameter vector or W star vector to get as close to y as possible, our observation vector. And those best projections come from projecting the y vector onto x, or the span of columns for x. So that's to say that the projection should be the predictions in this case will be orthogonal to the projection of y onto the span of x, and so that really means that our H vector, which is our x times our parameter vector, is going to be orthogonal to our error vector, right? So we should always have this sort of picture in our mind where we have some sort of y. I mean, I'll just do the same colors. We have our y vector, and we have the span of our x's with the parameter vectors, and that's what's giving us our so this in purple will give us our hypothesis vector, and the projection of that is what's orthogonal to the error vector, which the error vector is just in here, and that error vector needs to be orthogonal with respect to our hypothesis vector. Don't think about it as being orthogonal to y or anything like that. So always keep this picture. It's a very simple picture, and it doesn't convey the itself does not convey the idea of like multiple features and whatnot, because all that information is packed into this H vector. But keeping this picture in mind of that the error vector is orthogonal to H, and that's the thing that we're trying to minimize, and that's how we get to this becomes orthogonal whenever these W's, or this W vector is W star, the optimal vector. So that's what you want to think about, and those are the big things to take away from what we've done so far, and how we've tied together this idea of reconstructing the mean squared error in terms of these linear regression, linear algebra concepts, and then by doing that we have a new way of looking at the minimizer for our W, rather than using calculus, and now we're using the answer to the normal equations to do this. So that's the kind of the key concepts to take away so far, and it will set us up nicely for thinking about now multiple linear regression, which we will talk about next. Okay, so let's begin to kind of talk about multiple linear regression, and the next lecture we'll dive in further into this. But so far we've been working with departure hour and amount of time it took for us to go from home to school. And let's say that we want to add new feature or new attribute, new variable, day of month. Now, whether day of month is useful or not really doesn't matter at this point. It is probably it is almost certainly a horrible feature to use to try and increase our predictive power for this problem. But perhaps like a Boolean feature is weekend, right? Where this observation would tell us that this is a weekend or not. So this would be just zeros and ones. But we have day of month here. And so how do we actually do this? Well, if you remember, we have our design matrix that we created, which has our column of ones for W naught, and it has our x's. And now we're adding a new x, in this case, day of the month. So this is what we had before, and now we're just adding this. So our regression model needs to be able to, in order to solve for the regression problem, we need to be able to define now a W0 star, W1 star, and an additional W2 star. And we'll use that W2 star to multiply by our feature, which should be our X sub 2 in this case, day of the month, and we'll handle that in the design matrix. So it's important to know too that, well, when we look at the design matrix, we'll talk about that. So our hypothesis function, before, if you think back, like the first few lectures, our hypothesis function was just a constant model, which was just a straight line that fell on the y-axis, depending upon whatever x you had. Well, we got a little bit fancier, and we had a new hypothesis function that allowed us to define a line in 2 dimensions, because we had an intercept, y-intercept, and then we had a slope. And by adding another feature, we will go up in dimensions, and you have to think about it, but what happens after we have a line in 2 dimensions? So think about that, and what we have is a plane in 3 dimensions. And as we go up higher and higher in dimensions, we get into things called hyperplanes. And another thing that happens as we get into higher dimensions is that our data points start to move further and further away from each other, which makes using them for prediction even more difficult. This is called the curse of dimensionality. As we add more features and we build a more complex model, our data points in nth dimensional space get further apart. So this plane here is what our original line was in our linear regression. So in originally, where we had something like this, and then this was maybe our data points. This is the 2D case. Now this is the 3D case, where we've added on. Maybe this would have been commute time, and this would have been departure hour. So we've added on day of month. And of course, this plane is going to pass through commute time somewhere on that axis, and that will be our y-intercept. So I already talked about this, but let's think about it now. How do we actually design or update our design matrix? Like, what actually changes structurally? Well, we have our h vector, and our h vector is going to define our hypothesis functions for each of these rows. So that's going to give us a departure hour and a day, because these are the 2, you could say like the x1 and x2 are 2 features, and 1 is going to correlate to our intercept. And this is going to correlate to our x1 and our x2, and then the w, not w sub 1, w sub 2, is what we're trying to find to be able to solve this linear regression problem. And so we have to construct our design matrix by just simply adding another column, right? And this is where this is. So we have our ones from before, which are W0s. We have our first x sub 1, which depicts departure hour, and then we're going to add day as our x sub 2, right? Like, none of this changes, because x is just this big thing here, and x can be any number of features. It doesn't matter. Our y doesn't change. The only thing that would change our y if we were to add more data to this, because every row in y and every row in x corresponds to an observation in our data sets. So the only thing that changes is how deep x is, and it gets, we add more and more columns on for each new feature that we have. But our observation vector stays the same, and all we're doing now is adding 1 to our parameter vector as well. So we have now w, right? Like, these correspond to u0, w1, and now we have a w2. So our, I probably shouldn't do this in yellow, I'll do it in green. We have our u0, w1, w2, and that corresponds to our parameter vector. So these are the changes that need to be made to our setup in order to solve for the normal equations, which will give us our W star. So so this is what we're trying to figure out. Okay, I think this lecture has been long enough. So remember, the important thing here is that we link together the solution to the normal equations as a way to solve for W star. And this gives us a way to kind of out of the box very quickly have a minimizer for the new way that we're defining mean squared error, which is this vectorized matrixy way of defining it. And we've shown that by doing that, we're able to now generalize linear regression and add more features to it. So why is that important? Because even if your data set is only one or two features, you can engineer additional features. For example, you could take the logarithm of a feature, especially if you want to change the scaling of a feature. And there's all sorts of things you can do with that to add more features. I'll also say one last thing is that when you get your W's, another interesting fact that you'll learn is forget about your W naught, but think really about your W sub 1 and W sub 2. These are going to be essentially scalar values that are used to multiply through some column in your X. And you can really learn a lot from the linear regression model that comes out of solving the normal equations, or by minimizing mean squared error. And if your W, like one of your W sub 1s or sub 2s, winds up being very large, and another one winds up being very, very small. Like just for example, if we had a, it's fun if we had like if we had W1 and W sub 2, and we found that this is equal to like 25.211. This is equal to 5. We'd say that W sub 1, or the one that corresponds to, let's say, departure hour, we'll just say this corresponds to that, keep it similar. We'd say that departure hour is a very important variable because it winds up having a lot of weight in how this parameter changes, where day of the month is so small, it's negligible. You could get rid of this feature completely and it wouldn't really change your plane at all. In this case, because we have two W sub 1, W sub 2. So if this was the actual W's that we got out of this problem, we would want to most likely just get rid of W2 and refine the best fit plane and make our model simpler. Adding more features can be a good thing, but it can also be a bad thing. It really depends on the complexity of the problem you're trying to solve. And when you look at these parameter vectors, that can tell you a lot about how good this parameter is, or how good your features are, your X sub 1 or X sub 2. That's just a little side thing to note. And we'll look at more of the stuff in the class demos and the following lecture as well.